Okay, welcome to Uncertainty Principle 1, where I try to get at one of the fundamental concepts of the uncertainty principle that I've misunderstood at times. So this is Physics X, Fundamental Concepts in Physics, where I try to explain some of the coolest concepts as I understand them. Sometimes I say I don't teach truth. I bring people up to my level of misunderstanding. So I've been trying to do this for a while, and so sometimes my misunderstandings are still misunderstandings, but perhaps a little bit more thought out than people who haven't had thought for so long. So there's some pretty cool stuff here, though. So this is an online course, so you don't, even if you're just surfing around the web and seeing this, you can please feel free to click along. This is being taught for credit at Michigan Tech, and there is a studio audience in front of me of students hoping to get credit, some of them. Okay, so I like to phrase things in terms of questions because this brings things up very clearly in my mind because it makes me think things through. They're sort of like concept tests. So let's say you have a photon that goes through a narrow slit and then moves toward an image screen. Is it possible, even in principle, to predict exactly where this photon will impact that image screen? So you can think yes or no. So if you want to contemplate this, you can stop the video, and you might guess from the title of this talk that this is about the uncertainty principle, so the answer to this is no. And this is at the heart of the uncertainty principle. This is where quantum mechanics really differs from classical mechanics. In classical mechanics, you have balls rolling down inclined planes, you have things being thrown, and you can predict very exactly where things are. This is the world that we're most familiar with. We know, stresses on buildings and how long it takes for things to happen. And in our macroscopic world, things have very definite answers, and physics predicts very clear answers. This is what you're going to get when you do this. But in the usually small world of quantum mechanics, it is not, it's not a fault of anybody. It's not the fault of the equipment. It is fundamentally impossible to know exactly what's going to happen. And a very simple example of that is just having a photon go through a narrow slit. And it gets most interesting. So here you have a photon source coming here, and here you have your narrow slit, and here you have your screen. So when the photon has a wavelength, usually determines its color. So when it goes through here, if the width of the slit is on the order of the photon wavelength, then what you find out is that where this ends up is quite broad. And you can have photons hitting here, 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 where that's counterintuitive. And you can't tell where it's going to happen. You don't know where that photon's going to hit. If you do one photon and it hits here, and you say, okay, now I get it. The first photon hits here, the second photon's going to hit there as well. Not necessarily, no. It can hit anywhere in there. This is a probability distribution here, which means it'll usually hit near the center, most likely hit near the center, but it could be quite far apart from that. So this is the heart of the uncertainty principle and quantum mechanics, and it is strange, and it is counterintuitive, and it can even get stranger. So I'm going to explain that. Now here's the next one is a cool one. Okay, so here's another thought experiment. So consider this. A photon goes through the same narrow slit. Okay, so here's your photon source here. Could be a flashlight. Photon, another narrow slit here. And you have another screen here. So the photon then impacts the screen. Let's say it hits here. Is it possible, even in principle, to reconstruct both the position, which means it went through the slit, and the momentum of the photon when it passed the slit? This is a slightly different question. The first question was, could we predict where on the screen it's going to hit, where it's going to hit here? This is different. It's already hit the screen. Can we go back and say, where was it when it passed the slit? This is something I've contemplated for a long time before finding the answer. This bothered me a lot because I didn't feel when I took undergraduate physics that the answers were really telling me things like this. They were pretty much giving me mathematical formalism where I could calculate probabilities of things happening. So the answer to this may surprise many people. And people will say, oh no, you've really messed this one up. So with that ado, the answer is yes. You can reconstruct the position and the momentum of where that photon was. Let's quote Feynman. It is quite true that we can receive a particle and on reception determine its position, what its position is, and its momentum would have had to have been to have gotten there. That is true. But that is not what the uncertainty principle refers to. The uncertainty relation refers to the predictability of a situation, not remarks about the past. Okay? So this is a fundamental change from what I was thinking when I was an undergraduate. And it took me a while to actually track down someone famous who quoted things exactly like I thought they might have been. And that's the way it is. You can reconstruct. The uncertainty principle can, in a sense, be beaten in the past. Here's what it was. So if this thing, let's say you have photon here coming through, here's a slit, you can put this image screen way far away. And then the further away you put it, the more better you would have had to have known what the momentum was in order for it to get there. So it hits a little spot on that screen. If you move this screen way far away, then the photon would have had to have gone off at a very specific angle. And that very specific angle would give a very specific momentum along the slit in order to get that far. You could not have predicted at the time it passed the slit where it's going to go, though. Once it's been there, you can work back and say this is where it's been. Okay. So let's look at the fundamental uncertainty relation. It's delta x, delta p sub x is greater than h over 4 pi. Delta x, again, I like to think in terms of specific experiments, so the experiment, it's not confined to that. But the experiment I like to think of is, again, the single slit experiment. So here, if we think of that, this distance here, the width of the opening of the slit can be considered delta x. So when the photon goes to that, it has to pass through that slit. Consider that the slit screen is opaque. If it hits anywhere else in the slit screen, it's just reflected or absorbed. If it goes through that slit, then we know that this distance here, consider the x-axis here to be up and down, it had to have been in that space delta x. Okay? So that's one of the variables. Again, in terms of the single slit experiment, what's delta p sub x? That's the uncertainty in how fast it was moving up and down. Not really what p is, which is its total momentum, which could have been in this direction. That's not, what's really unknown is its up and down momentum. And it's its up and down momentum that's going to tell it where it's going to be on that screen. So if it comes here, down here, if it hits down here, then it had a p that was down in this direction. If you thought that delta p, if you tried to make delta p 0 when the photon moving this way, then delta p goes around 0, so delta p is p, and so down here that tells you what p was. So again, to requote, many times in physics texts I see quotes like here, this is not an exact quote, no one can predict the exact position and exact momentum of a particle at the same time. Can know well, you can't predict it is really what they should be saying more clearly. You can't predict both its delta x and delta p. If you want, you can just go after delta x and make this slit opening infinitesimally small. And then you'll know, oh, I know what delta x is. But you find that the smaller you make it, the wider the delta p is. It fans out more. So again, uncertainty principle is about predictions. Okay, so I will typically ignore factors like 4 and pi because it's not easy for my presentation software to include them without significant work. So I will say order of magnitude h, which is Planck's constant. So Planck was one of the first people to really think about concepts like this. Being an order of magnitude person, 4s and pi's don't usually bother me. I like concepts and things like that. So how do we get Planck's constant from the uncertainty principle? Well, photons have an energy of hc over lambda. So that if you wanted to compute the momentum of a photon, it would be h over lambda. So If you wanted to, if the momentum you thought was 0, it might have a uncertainty then of h over lambda in magnitude. Although you have to be careful about the way I phrased things before. Another thing is that how accurately can you know the position of a photon? It's roughly the wavelength of a photon from measurement. So you multiply those two, the lambda goes away, and you're left with Planck's constant. So here the order of magnitude of the uncertainty is on the order of the, is considered to be on the order of the momentum of the photon itself. Okay. So one fundamental way this is phrased is objects can act as waves and particles at the same time. But the measured limitation of one type of behavior must come at the expense of the fundamental predictability of a complementary type of behavior. So in some sense, it can act like a photon can act like a particle, and then it's sort of like a bowling ball, and you know where it's going to go. But that comes. But they cannot act, well, must act as a wave and a particle at the same time. They can act. And if you measure one behavior, you limit the other. Okay, I'm sorry about the font here. I've tried to change it. So here's another fundamental concept. Is the uncertainty principle due solely to the act of observing? So I always hear this. In fact, I just ran into it recently. Yes, when you observe something, you must disturb it. Is that the root of the uncertainty principle? Or no, you can observe something without disturbing it. You're fine with that. Which one is it? Is the uncertainty principle based on disturbing things because that's what has to happen when you measure it? Stop it if you want. Here's the answer. You can observe something without disturbing it. The observer effect is not fundamental to the uncertainty principle. And this was really highly debated by people like Einstein and Bohr way back. In fact, Heisenberg, when he coined his own uncertainty principle, thought pretty much, we think, that disturbance was the fundamental root of it. But now we know that's not true. Entangled particles are one way to disprove this. You can measure one of two entangled particles, which we will get to entangled particles in the future of this course in some detail. So you can learn things about the other particle without measuring it at all. You don't have to disturb that other particle. The other particle, all particles, will still obey the uncertainty principle regardless. And there's another way to do this. It is the Renninger negative result experiment. So let's say you have an alpha particle decays in a random direction. It is surrounded by two half spheres. Then after the decay, the particle does not hit the nearby half sphere. Therefore, without measuring anything directly about the particle, without disturbing the particle, you know that particle will hit the other half sphere. And it's a very simple experiment, but it gets to the root of whether the uncertainty principle is based on disturbing particles or not. And it is not. And with that, I will close with what I've told is an annoying close, but I'll do it anyway. Please keep Schrodinger away from your cat. And we'll be back with more uncertainty principle next time. Thank you. Talk that this is about the uncertainty principle, so the answer to this is no. And this is at the heart of the uncertainty principle. This is where quantum mechanics really differs from classical mechanics. In classical mechanics, you have balls rolling down inclined planes, you have things being thrown, and you can predict very exactly where things are. This is the world that we're most familiar with. We know, stresses on buildings and how long it takes for things. Okay, welcome to Uncertainty Principle 1, where I try to get at one of the fundamental concepts of the uncertainty principle that I've misunderstood at times. So this is Physics X, Fundamental Concepts in Physics, where I try to explain some of the coolest concepts as I understand them. Sometimes I say I don't teach truth. I bring people up to my level of misunderstanding. So I've been trying to do this for a while, and so sometimes my misunderstandings are still misunderstandings, but perhaps a little bit more thought out than people who have through. They're sort of like concept tests. So let's say you have a photon that goes through a narrow slit and then moves toward an image screen. Is it possible, even in principle, to predict exactly where this photon will impact that image screen? So you can think yes or no. So if you want to contemplate this, you can stop the video, and you might guess from the title of this, I haven't had thought for so long, so there's some pretty cool stuff here though. So this is an online course, so you don't, even if you're just surfing around the web and seeing this, you can please feel free to click along. This is being taught for credit at Michigan Tech, and there is a studio audience in front of me of students hoping to get credit, some of them. Okay, so I like to phrase things in terms of questions because this brings things up very clearly in my mind because it makes me think things